Wow, I can't believe it's our last day of notes in Math 081. Well, so we have 3 semi-short lessons to do on this last day. One of them is similarity and proportionality. The other one is square roots. And the last one is Pythagorean theorem. So those will be our last 3 lessons of Math 081. And be sure and read your emails. I sent out several updates for the upcoming week, when your final is, and so on. So make sure and read your Canvas email. Okay, let's go ahead and get started. So, similar. What does similar mean? So when I think of similar, I think of building model cars that look exactly like a big car, or model airplane, something like that. So that's how I think of similar. It's just a scaled down version of something larger. So the figures below, the figure on the left is similar to the 2 figures on the top right, but is not similar to the 2 figures on the lower right. So in order to be similar, they have to retain their shape. So yes, this is a smaller version of that, and it's retained the shape, as is this. This one has been stretched out, this one's been stretched up. So because they haven't retained their original shape, they would not be considered similar. So they have to retain the shape and just be small, scaled down versions of the original in order to be similar. So to answer this first question, it says, how is the relationship of the similar shapes to the original different? So the similar shapes have retained their shape. Similar shapes have retained the original shape. I'm not sure why this is not a very good picture. It's a little bit blurry, but hopefully you guys can see okay. Informally, we say that 2 figures are similar if they have the same shape, but are not necessarily the same size. So this is the definition of similar. So they have the same shape, but not the same size. We can think of similar figures as scale drawings of each other. We can still consider shapes to be similar, even if we need to turn one around or flip it to make it look like the other one. And you'll see some examples of this on the next page. Okay. So according to our definition of similar, let's go down here and look at our different shapes. Oh, this one's a lot better than the last page. So have we retained the shape? Yes. So all that's different is the size, right? So I would say this is a yes, and shape is retained. And what about the little kidders? This one's kind of gotten fat, hasn't it? It hasn't retained that original shape, so this would be a no. Shape is not retained. And I'm just going to quit writing this every time, but now you know what to write if it's a yes and what to write if it's a no. Because this is kind of a longish lesson, so we're going to zip through it. Not zip through it, but this easier stuff. So this one, has it retained the shape? Now, remember how on the other page it says it's okay if you have to turn it to make it look like that? And if you turn it, It looks just like the original one, right? But just a smaller version. So this one would be a yes. Having to flip it is no big deal. It's when you can't make it look like that one that it's a big deal. So what do you think here? This appears to be close to a right angle, but look at, I don't have a one that appears to be close to a right angle, so that would be a no. What should we say? Different types of triangles. So one appears to be an isosceles non-right triangle, and one appears to be a scalene, all sides different, right triangle. So they're different types of triangles. This is what I let my students in geometry write instead of triangle all the time because they had to write it so many times. Some of them even put the S inside the triangle. I thought that was kind of cool. So different types of triangles. So that's a no. Now we do have two triangles that do look to be right triangles, both of them. They both look to be scalene. So I would say, yes, this is a scaled down version of that one. So same type of triangle. Okay, one more page and then we'll move on to the math stuff after we get these definitions down. So page 3 of module 4, lesson 8. So this appears to be a rectangle and this appears to be a square. So do you think a rectangle can be similar to a square? No. They are different kinds of figures. And we don't know for sure they're a square or rectangle. If they put a right thing there and did this, then we would know. So different kinds of figures, but just from the picture we can kind of tell. So we could say square appears to be square, right? So squares and rectangles cannot be similar to one another. A square can only be similar to another square, and a rectangle can only be similar to another rectangle. Whoops, not square and rectangle. There we go. And now it looks like we have two rectangles. So that would be a yes. Same kind of figure. So they appear to both be rectangles. And the last one, this one tricks a lot of students. This is a yes, because if you turn this triangle around, so look at this one. Now look at this one. See, they look to be the same. This one's just turned around from it. So there's that one. There's that one. So yes. And it's okay if they can be turned around. That's what it said on page 1. It says, we can still consider shapes to be similar even if we need to turn one around or flip it. So absolutely. Yeah, we don't need to write that. Okay. Let's go ahead and move on to the math part of this. So now we know how to identify similar figures. Most of the time they'll tell you too that they're similar. So similar figures. So we're going to learn that similar figures have sides that are proportional. So there's a scale factor that we can use to go from one to the other. So for instance, looking at this, if someone tells me these two are similar, well, let's go ahead and read through the paragraph. I shouldn't jump right in, right? When we have two figures that are similar, we can think of them as scale drawings of one another. What this means is that there is a constant multiplier from one object to the second. And you can call that a scale factor. That's what most people call it. For example, in the similar rectangles below, so they're telling us they're similar, and they do have to tell us because we can't really assume it. The width of the larger rectangle is 3 times as large as the width of the smaller. This means that the length must also be 3 times. So looking here, you can see 2 times 3 is 6. And remember, this only works if they're similar. If they're not similar, then this won't work. So that means this one times 3 must give me that side if they are indeed similar, so we can see the question mark is 12. So that is called using a scale factor, which means if they're similar, you're going to multiply the corresponding sides by the same number to get the other figure. So in this figure, the question mark is 12. So in math words, because I know you guys all want to speak like mathematicians, we say the lengths of the sides of similar figures are proportional. So what that means is we can do 4 over 2. Oh, I guess they do it down here. Never mind. So to get that aspect ratio, which is what we get when we divide our sides, we do 4 over 2. That gives us 2. We found this side to be 12 above. 12 over 6 is 2. And that's how we can test and make sure our work is right, is we can compare these are called ratios. So the ratio is called a comparison between two numbers. It's really just a fraction. So 4 over 2 should be the same thing as 12 over 6. And you're going to learn later, we could also say 4 over 12, which is 1/3, is the same thing as 2 over 6, which is 1/3. But for right now, they want you to stay with the same figure because they're talking about aspect ratio. So the length divided by the width is 2. The length divided by the width is 2. So another important relationship is that the ratio of the sides in each figure must be the same. So that's what it's called, the ratio of the sides. Now we look at the relationship between height and width. So height to width 2, height to width 2. And apply similar reasoning to the scaled figure. We can see that the height is twice the width in the original figure, so the height of the scaled figure must be 2 times the width as well. So the height of the scaled figure must be 2 times. Yes. Okay. So any similarity problem can be solved by setting up a proportion. So that's why we said that they're proportional. And we had a little bit of this in Module 3. So this should be, remember how you had gas to miles, gas to miles? Remember all those proportions we did in Lesson 9 together in that really long video? Yep. So we can do the same thing with similar. So we can say, when we're looking at this picture, I'm going to draw it just so we don't have to keep turning back. So they gave us that this was 4 and this was 2. And then on the big picture, they gave us that this was 6 and they called this the question mark. Well, we're going to call the question mark X. So you can say 2 goes with 6, just like 4 goes with X. So left over right, left over right. And also you could have done it like this. 4 over 2 equals X over 6. Because a lot of students think, oh, there's only one way to set up a proportion. That's not true. What is true, though, is you have to be consistent. So if I have the left side on top and the right side on the bottom, I need to have the left figure on the top and the right figure on the bottom. Or this one, height to width, height to width.